In section 4.5, we're solving exponential and logarithmic equations by applying what we've learned about exponential and logarithmic functions. Part of what we learned was that when the bases are chosen appropriately, these functions will be one-to-one, and we can use that one-to-one feature, if possible, in order to solve some exponential and logarithmic equations. Recall the definition of one-to-one is that if we choose a y value, there is one and only one x value that is associated with that y. Okay. So for any value of the output, okay, that is the y value, such as a y value in the range, there would be exactly one input that would lead to that output. So here's an example where we could use that, for instance, in an exponential case. Suppose that we have an equation 2 to the x is equal to 8. Well, since 8 can be written as 2 to the power of 3, then we can rewrite the equation as 2 to the x is equals 2 to the third. And in that case then, since both sides have the same base, the base of 2, then it would be that x has to equal 3. The reason that that is going to be the one and only solution to this equation is because the function f of x equals 2 to the x is one-to-one. Consider the graph. F of x is equal to 2 to the x. That's an exponential growth function. Looks sort of like this, right? When we say that the function is one-to-one, we know graphically that we can test to see if it's one-to-one by doing the horizontal line test, which is, of course, as you know, you can draw a horizontal line anywhere within the range, and so that is us choosing a y value. Right? Y is equal to a constant for any horizontal line, and if that horizontal line, as long as we choose it within the range, if we see that it only ever intersects the graph in one location, no matter what horizontal line we choose, then we declare the function to be one-to-one, hence it's going to be invertible, right? Well, so this is how we're applying it here. So we have the function f of x is equal to 2 to the x, and we are saying to solve the equation 2 to the x is equal to 8, we're saying that we're choosing the y value to be 8. So we can imagine the horizontal line with the equation y is equal to 8, which, because this function is one-to-one, that line y equals 8 can only intersect the graph in one location. That is, that there is only one x value that could have led to that value of y, because we have a one-to-one function. So how do we find out what that x value is? Well, in the equation what we said is if we can sort of guess, or if we can figure out by some other method what the exponent would have to be for the chosen base of 2, then we know in fact the one and only value of the exponent that it could be. So the idea is, if we can make the base the same base on both sides of the equation, then we can simply set the exponents equal to each other. That's using the one-to-one nature of the function, right? If the bases are the same, then the exponents would have to be the same, because the function is one-to-one. So the same approach can be used. Oh, by the way, of course, this would just be x is equal to 3 for this function, right? The same approach could be used in a logarithmic example. Let's say, for instance, we had the logarithmic equation. How about the log base 3 of x is equal to the log base 3 of 5, for example. Okay? We have the same base logarithm on both sides, just like we were able to have the same base of the exponential on both sides here. And therefore the arguments can be set equal to each other, and that solves the equation. This is the one and only solution to this particular equation because of the one-to-one nature of the function and the fact that this creates a linear equation when we set those arguments equal to each other. Okay, take a look at the graph of the function that we're analyzing here. This is the function f of x is equal to log base 3 of x. It's a logarithmic function where the base a is equal to 3, and that's greater than 1. Okay, so it's the graph of this logarithm, recall, can be constructed by inverting the exponential function that would have had a base 3. So if we think of f of x equals 3 to the power of x, which is a growth function, right, the inverse of that graph would be the graph of this logarithm of base 3. And so it looks something like this. All right, it crosses at 1. Okay, the x-axis, it has the vertical asymptote, and the vertical asymptote is found at x is equal to 0. Okay, because the growth model had a horizontal asymptote at y is equal to 0, for example. All right, so here's our graph. This is a one-to-one function, right? And we're saying if we want the output to equal whatever log base 3 of 5 is, if we choose the output to be the y is equal to log base 3 of 5, okay, that would be graphically represented by a horizontal line, and that horizontal line is going to intersect our curve in only one location because it passes the horizontal line test. And what would be the associated value of x? Such that the output would be log base 3 of 5. Well, the function is log base 3 of x. So the value of x that we should choose would have to be 5. That way when we plug it into the function, we get log base 3 of 5. So x equals 5 is the one and only value of the input that can result in that output. Okay, so the idea is if you can get the same base logarithm on both sides of the equation, and there's only one term on each side, by the way, there's a single log equal to a single log, and they both have the same base, then you can set the arguments equal to each other and proceed from there. Notice in each case, this just gives us a different type of an equation. We've converted an exponential equation in each of these cases into just a simple linear equation. Okay. They're not always going to be quite this simple that you're just going to have x is equal to a number. Okay, the idea is that you have the same base on both sides, then you can set the arguments equal to each other. Take a look at another exponential example of this type. Solve the equation 9 to the power of 3x minus 4 is equal to 1/9. Okay. So on the left-hand side, we already have something with a base of 9. And on the right-hand side, we have 1 over 9. Well, 1 over 9 can be rewritten with a base of 9. Because 1/9, we can rewrite it as 9 to the negative 1. That's part of the strategy of using the one-to-one property of the exponential function. If you can write both sides of the equation with the same base, then you can set the exponents or the argument equal to each other. If you can't write both sides with the same base, then you can't use this strategy, and you would use the more general strategy that I have listed above that we'll take a look at in a moment. Okay, so we're able to write both sides as 9 to some power, and therefore we can simply set the exponents equal to each other. And notice that in this case gives us a simple linear equation that we can then solve for x. 3x minus 4 is equal to negative 1. So I can add 4 to both sides, so 3x is equal to 3, divide by 3 on both sides, and I get x is equal to 1. And we can check the answer by plugging it in. 9 to the power of 3 times 1 minus 4, okay, is that equal to 1/9? Well, let's see, this is 3 minus 4 is negative 1, okay, so 9 to the negative 1 is equal to 1/9, yes, that's true. So we were able to solve this exponential equation by setting both sides of the equation, right, equal to an exponential with the same base. Let's take a look at another example. 25 to the power of x squared minus 4 is equal to 5 to the power of 4 minus x squared. Okay. All right, so the left-hand side is an exponential with a base of 25, and the right-hand side is an exponential with a base of 5. Okay, but both of those bases can be written with a base of 5. If we choose to, right? Because 25 can be written as 5 to the power of 2. Okay. So if we use that on the left-hand side, we can rewrite the left-hand side as 5 squared to the power of x squared minus 4. And the right-hand side already has a base of 5, so we have 5 to the power of 4 minus x squared. Now we can use a rule of exponents. That rule of exponents would be, for instance, if you had something like a to the power of m, which is then to the power of n, that would equal a to the power of m times n. You can multiply the exponents together. So the left-hand side, we would have 5 to the power of 2x squared minus 8, and that would be equal to the right-hand side, which is 5 to the power of 4 minus x squared. So now we have both sides written as a single-term exponential with the same base, the base of 5. And therefore, we can set the exponents, that is, the arguments of each side, equal to each other. All right, and this results in us having what looks like a quadratic equation now. And so then we just proceed by solving the resulting quadratic equation, which we already know how to solve every quadratic. Right? I can add x squared to both sides. I get 3x squared. I can add 8. So I get 12 over here. Divide by 3. X squared is equal to 4. And then solving for x, we get x is equal to plus or minus the square root of 4. That is plus or minus 2. Let's be sure to check the answers here. Let's make sure that this worked. Okay, let's check. Start by checking x is equal to 2. And I'm going to check it back in the original equation that we had up here. Okay, 25 to the power of, let's see, 2 squared minus 4. Does that equal 5 to the power of 4 minus 2 squared? Well, this is going to be 25 to the power of 0. And that equals 5 to the power of 0. And that's true because each of those would equal 1. Okay, so x equals 2 works. And in fact, we see we're going to get the same conclusion if we plug in x is equal to negative 2. Right? No difference there because we're going to be squaring the negative 2. Gives us the same result as squaring 2. 25 to the negative 2 squared minus 4 is equal to 5 to the power of 4 minus negative 2 squared. We're going to get exactly the same result. Right? We're going to get 1 is equal to 1. So it worked. We got x is equal to plus or minus 2. Now, that's not the only way to be able to solve this equation. The more general strategy is also going to work here. The more general strategy is to solve an exponential equation, you would use logarithms. Okay? And then, by the way, solving logarithmic equations, in general, you would use exponentials. That is, you can convert between the logarithmic and the exponential forms. Remember the way to convert between those two forms. In general, if you have, for instance, the equation, there you go, the exponential equation y equals a to the power of x, okay, that can be rewritten in the logarithmic form, okay, as the log with the base of a. Remember that the base of the exponential and the base of the logarithm must be the same as each other when doing the conversion. And remember that the logarithm will always be equal to the exponent of the exponential. So we have the log base a of y is equal to x. That would be converting from exponential form into logarithmic form. And we can do the reverse of that. Suppose that we are starting with the equation y is equal to log base a of x. Okay? If we wanted to convert that into the exponential form, we do so by determining what the base is, and the base here is a, the same base as the logarithm. Okay? And the exponent is, again, what the logarithm is equal to. So the exponent would be y. And then a to the y is going to equal the result of x. Okay? So a to the y is equal to x, and that would be converting from logarithmic form into exponential form. So this is the general technique that we're going to use to solving either exponential equations or logarithmic equations, is by converting into the other form. Okay? Now that's going to require that we are isolating either an exponential term or isolating a logarithmic term. So we're going to take a look at a variety of examples whereby we can do exactly that. Isolating an exponential term, then applying the logarithm, that is converting into logarithmic form, and then possibly using laws of logarithms to solve. The law of logarithms that is going to be most applicable here might be where we apply a logarithm and then we pull the exponent to the front, that is, express the exponents as factors. That is, rewriting an exponential as a product of factors. Okay, then you can reassess the equation there and see what kind of an equation you're left with now. Is it linear? Is it polynomial, for example? Is it a rational equation? And then you can proceed with it from there. Okay, for the logarithmic equations, again, you might have to combine the logarithms by using laws of logarithms. That is, combine into a single logarithm. And then you can convert into the exponential form and then assess what the equation looks like once it's written in its exponential form. And that again might be a linear equation, a polynomial equation, a rational equation, for example, and then we could proceed based off of what that form looks like. There we go. Okay, so converting from exponential to logarithmic form and back again. So we could have applied the general strategy in either of these cases down here. I'll just show you, for example, let's go down to this example right here. We could have solved this by applying a logarithm, that is, converting this into the logarithmic form. Okay. Let's take a look at that. Clear some space here and apply the general strategy. So we have already isolated the exponential term. Right? 9 to the 3x minus 4 is equal to 1 over 9. Okay, we have already isolated the exponential. That is, this term right here is the exponential. Okay. And so what we can do is we can convert this into a logarithmic form, right? It is something of the form right now. It is already written something of the form a to the power of x is equal to y, right? Where instead of x being the exponent, we have the expression 3x minus 4. Y is equal to 1/9, a is equal to 9. So we can convert that into logarithmic form. We can either do so directly, that is, we can rewrite it as log base a of y is equal to x. Right? So in this case, that would be converting it into a logarithm, right? Where the base of the exponential was 9. The exponent goes on the other side of the logarithmic equation, so that would be 3x minus 4. And the result of the exponentiation, which in this case was 1/9, becomes the argument of the logarithm then. Okay. We also could have achieved this result by applying a logarithm of base 9 to both sides of the equation. Right? We would reach the same conclusion. Okay, so let me go up here to this step. Let's say I applied a logarithm of base 9 to both the left-hand side and the right-hand side of this equation. All right, there's 3x minus 4, and then on the right-hand side, a log base 9 of 1/9 over there. Notice then, by the property of logarithms, we now have the base of the logarithm, which is the same as the base of the exponential, and that's the way that we designed it. And we recall that when that's the case, that means we get to cancel out the logarithm with the base of the exponential. So we'd be left with 3x minus 4 is equal to log base 9 of 1/9. And that's exactly the same conclusion that we got here anyway. So we can reach this result right here. Okay, we can reach this equation right here, the logarithmic form, by either converting the exponential form into the logarithmic form or applying a logarithm that has the same base as the exponential to both sides of the equation, and then simplifying from there. Okay? So the property that I used right there was the one that was log base a of a to the x is equal to x. That's where the base is the same. Right? That's why they got to cancel each other out. And so we're left with just the exponent isolated. All right, so now we're left with what is the log base 9 of 1/9. Okay, well, that you can evaluate by hand. You can also do it on the calculator. Recall that to go to the calculator when you have a base that is not 10 and then is not e, you would need to use a change of base formula. So you could do that. Okay. Or you can also, again, you could just do this by hand, because we can rewrite 1/9 as 9 to the power of -1. Okay? So then we get to use this property again. If we rewrite it this way, again, we get to cancel, right? The logarithm with the base of 9. So we have the equation -1 is equal to 3x minus 4. In any case, we end up at this same result. If it's possible to convert both sides of the equation to have the same base, you might find it's a time saver, and that's why I wanted to make mention of that approach. That in general you can apply logarithms or convert into logarithmic form, but in many cases that's going to be the lengthier approach if it was maybe possible to convert both sides in the same base, and that's why I wanted to mention it. You're going to get to the same answer in the end anyway. And you may as well practice all these techniques, okay, so that then you have a variety of approaches that you can use, okay, so that you can build an intuition about when one approach might be preferable versus another approach. Okay. All right. So, how would that have looked if we applied it to this example right here? Right? Could we convert this into the logarithmic form? What would that look like? Well, just get that rewritten in the logarithmic form. So we had 25, okay, 25 to the x squared minus 4 is equal to 5 to the power of 4 minus x squared. That was the original equation. Okay. Let's say we wanted to apply a logarithm to both sides. We can really choose any logarithm, any base logarithm we want because of the law of logarithms that says that we can take a log of, of one base onto an exponential of a different base, and it's going to allow us to pull the exponent to the front, right? So really we can choose any base logarithm we want here. It doesn't matter, okay? But I may want to, for convenience, maybe choose a base logarithm that would allow us to cancel at least one of these two bases out. So I'm going to choose a base 5. You could choose a base 25 if you want. You can play around with different techniques and see that you'll get the same answer anyway. Okay, so I'll apply a base 5 logarithm to both sides of this equation right now. Okay, so log base 5 of the left and log base 5 on the right. Okay, and that's going to serve the purpose of on the right hand side, it's going to reduce the right hand side to just 4 minus x squared because we get to cancel out the logarithm with the base of 5 right there. Okay, and on the left hand side though, we're left trying to figure out what this is going to equal. And the way to simplify that, well, one way to simplify that would be what I suggested above, which is to convert the 25 into a base 5 number. Okay, so we get log base 5 of 5 to the power of 2x squared minus 8. Once we rewrite it that way, we get to use that same property of logarithms that allows us to cancel here. And we'd be left with 2x squared minus 8 equals 4 minus x squared. We would be right here again, back at this equation. And then we would proceed solving from there. Okay, so we're going to end up at the same solutions anyway, regardless of which technique we use. But if it's possible to convert both sides to have the same base, we can set the arguments equal to each other. That's the point. Okay, and that's using the one-to-one property. Let's take a look at some more examples now. We should take a look at a logarithmic example. How about? All right, so let's say you want to solve. Here's a good question. Okay, for what value of x would it be true that the log of x plus 5 is equal to the log of x plus the log of 5? Note, this is not true in general. You cannot distribute a logarithm. Okay, I'm even going to make that note right here. Note, the log of, let's say, a plus b does not equal the log of a plus the log of b, okay, in general, right? In fact, what's actually true is that the log of a plus the log of b actually equals the log of a times b. That's law 1, the law of logarithms, from the law of logarithms, right? That statement would be true, not the log of the sum is equal to the sum of logs. That is not correct. However, that doesn't mean that this is never true. I'm just saying that it's not true as an identity, right? This is not an identity here, but this one is an identity. Okay. This one's an identity. That is an equation or a statement that is true for all values for which it is defined. Now this equation right here is not true for every value of x that is in the domain, but it might be true for one or more values, and we're being asked to find the value of x which would make this statement true right here. How do we find it? Well, one way we can find it is by setting both sides equal to an expression, a single term, with a single logarithm of the same base. The left-hand side is already a single-term logarithm, the log of x plus 5. The right-hand side we can write using this law right here as the log of x times 5, or I'll write the log of 5 times x. Right? So we can use that law in order to simplify the right-hand side, right? We have now just combined into a single, okay? We've combined into a single log, and we required the same base in order to combine them, right? Okay, so this should have been the log base a, right, in general, like that. They have to have the same base in order for them to combine. All right, once we have it written like this, notice we have a log of something is equal to the log of something else. And they have the same base, so we can use that one-to-one property. That is, we can set the arguments equal to each other. X plus 5 is equal to 5 times x. Okay? Now notice we just have a linear equation here, and we can solve that linear equation pretty easily. Subtract x from both sides, we get 5 is equal to, subtract x from both sides, we get 5 is equal to 4x. Divide by 4, we get 5/4 is equal to x. Okay. 5/4 or 1.25 if we want to write it as a decimal. Fine, either way. Okay. So we found the one value of x such that this logarithmic equation would be true. You can check by plugging it in, okay? And in general, check your logarithmic equations because they do have restrictions on their domains. So you want to check logarithmic equations for extraneous solutions, okay? All right, the domain, okay? The domain for this equation right here, we have to have that the expression on the left has the same domain as the expression on the right. Their domains need to overlap each other. Well, the domain for the expression on the left is that x is, right, is that x is going to be greater than -5 because x plus 5 has to be greater than 0. On the right, the domain would have to be that x is greater than 0, and the intersection of the two, okay, the intersection of the two then would be that x has to be greater than 0. So the domain is from 0 to infinity. So any value of x that we get by solving this equation is going to have to be within this domain. And the value of x we got, 1.25, is in that domain, so it seems reasonable that it would be the solution, possibly. But we really should check by plugging it into the original equation just to verify that it actually is going to work. Okay? So, could we have used a more general strategy to solve the equation? Absolutely, we could have. This is what it would look like. Log of x plus 5 is equal to the log of x plus the log of 5. I mean, and again, in order to use the more general strategy, we want to isolate the logarithm. Okay, that's how we want to start. Isolate the logarithm. But there's right now 3 logarithms in this equation to discuss. So isolating it would require that we in fact put all the logarithms on one side to get them all grouped together. Okay, log x plus 5 minus the log of x minus the log of 5. And then that leaves on the right hand side would just be 0. Okay, and now in order to get it isolated further, we actually have to combine. Okay, combine into a single logarithm. Okay, how is that done? Remember the law of logarithms. So we have, first of all, we had the sum of logs is equal to the log of a product, but the difference of logs, Okay, we recall that one as well. Log base a of a minus the log base a of b, okay, is equal to the log base a of the ratio a over b. Okay, so we need to use that law as well as the sum law. So these combine into the single logarithm that has a base 10 because all of these had the base 10 logarithm. Okay, we can say that the x plus 5 is going to be in the numerator, and both 5 and x would be in the denominator. Right? Recall that if the logarithm has a negative coefficient, then the argument would show up in the denominator when we combine the logarithms. If we think that logs are exponents, that gives us a justification for why that is the case. Anything with a negative exponent, we would expect to take the reciprocal of, so it would show up in the denominator. So the left-hand side we have combined into this single logarithm, and the right-hand side is just equal to 0. Now we have logarithmic form. We have isolated the logarithm at this point. Okay? That's what I mean by isolating the logarithm. We have a single logarithm now written in this equation. So we now have an equation of the form log base a of x is equal to y. It is in this form. Okay. Of course, a happens to be 10. What I'm writing as x right here is actually the expression x plus 5 over 5x, and what I'm writing as y here is actually 0. We can convert that into the exponential form, okay, by doing a, the base, to the power of y is equal to x. All right, a to the power of y is equal to x. The base is here. The exponent is what the logarithm is equal to. And the result of exponentiation is the argument of the logarithm. Right? So we were able to do that conversion. Okay. Already we see this looks like more work to do it this way than it was to just equate the arguments by saying they both had the same base on both sides. And that's why I would prefer that approach, if it's available to us, to just get the same base on both sides and say the arguments are equal to each other. I see it as less work to do. Okay? But it's not always going to be available to us to be able to do that. Okay? But it's worthwhile also to get the practice of the general strategy. So converting this into its exponential form, well, let's take the base, and the base here is, of course, 10, raising that to the power of 0, and we would get that would be equal to the argument of the logarithm. So 10 to the power of 0 is equal to x plus 5 over 5x. We've now converted this into its exponential form. Note that although we've converted this into its exponential form, that does not mean we have created an exponential equation. Right? The equation that we're left with here is not exponential. It's not because the exponent that we see is not a variable. It is a constant. So converting it to exponential form does not mean we will be solving an exponential equation. It means that we're transforming the equation, and then we reassess to say, well, what kind of an equation do we have now? And the type of equation we have now in this form is in fact a rational equation. Right? We have polynomial over polynomial, and we have the left-hand side is just a constant. Okay, so let's solve this as a rational equation then. First, I'm going to simplify the left-hand side. 10 to the power of 0 is just equal to 1. So now I'm going to solve 1 is equal to x plus 5 over 5x. I would like to make a note of the fact that the domain of this rational equation is that x is not equal to 0. Is that the same as the domain of the original equation? It is not. The domain of the original equation is that x had to be greater than 0. In other words, x is not allowed to be negative for the equation we're solving. We've lost that information by rewriting this as a rational equation, but it's still true. X is not allowed to be negative. So if we were to solve this equation from here, we still want to check our answers in the original equation, the one we started with. Okay, because that's the one where we might find extraneous solutions. All right, so we've lost information about the original domain by converting this into a different form. That's why we check our solutions. All right, solve this by multiplying both sides by 5x. So 5x is equal to x plus 5. Here's our linear equation, and in fact, this is the same linear equation that we were just solving earlier. 5x is equal to x plus 5, right? That's the linear equation we're now solving. And so we already know what the solution of that is going to be. X is equal to 1.25. Okay, or 5/4. Right, and again, we can check the solution. Okay, make sure that we got a correct solution and that we didn't achieve an extraneous solution. That is, that we did not solve correctly, but still end up with an incorrect solution. That's what extraneous is. If you solve correctly mathematically, but you still have a solution that doesn't satisfy the original equation. Okay, so it would be possible to apply the general technique in this example. Okay. But I would say that it takes less time and less space on the paper in order to apply the one-to-one property. So be on the lookout for opportunities to be able to do that. But the general strategy is going to work on a wider variety of examples. And let's take a look at some more examples right now. Solve the equation. Let's see. 2 to the 1 minus x power is equal to 3. So here, we don't have the option to easily convert both sides to the same base. Now, if the right-hand side were something that could be written with a base of 2, then we would go with that approach. But 3 cannot be easily written as something with a base of 2, because 2 to the x is equal to 3. How would we find the value of x? We're going to have to apply logarithms, or in other words, convert this into the logarithmic form. Okay, let's say that we did converting into a logarithmic form. Okay. Convert into logarithmic form. We have an exponential, okay? That is something of the form, right? A to the x is equal to y. And converting that into logarithmic form, we would get log base a of y is equal to x. Right? It's always equal to the exponent. So in this case, converting this into logarithmic form, we would choose a logarithm whose base is 2, the same as the exponential. Okay? It is always going to equal the exponent, so that would be 1 minus x, and it is the result of exponentiation that we're taking the logarithm of. So we would have this equation, log base 2 of 3 is equal to 1 minus x. And then we can solve this equation for x. I'm going to solve it by adding x to the left-hand side and subtracting the log base 2 of 3. So x is equal to 1 minus log base 2 of 3. Okay? This right here is an exact answer. Okay? And that's one form of the answer that we should be looking to solve for. This would be what the exact answer is. Okay? Now let's go on and let's find an approximation answer. Well, what if we wanted to approximate this to, let's say, maybe, how about 6 decimal places? Let's do that. Okay. Approximate to 6 decimal places this solution. How could we do that? Well, this would require that we are able to access the calculator. And to do a base 2 logarithm on the calculator is going to require we use the change of base. So we can do, for instance, a base 10 log. That would be where we use the log of 3 over the log of 2. That's change of base. Okay. We've used change of base there. Okay. Another change of base that we could have chosen is if we use a natural log, because that also shows up on the calculator. So that would be if we had 1 minus the natural log of 3 over the natural log of 2. Okay? These are both change of base. In either case, we can then go to the calculator and we can get an approximation right now. So you can check on your calculator to see what you get, regardless of whether you use a base 10 or a base e logarithm. In either case, you should get exactly the same answer. And I'm going to round that answer to 6 decimal places. So I'm getting that this is approximately negative 0.584962.5. So to 6 decimal places, because the 7th decimal place is a 5, I'm going to round up. So I'm going to get negative 0.58 4963. And so that's our approximation. Okay. Now, I want to take a look at how we might have achieved that result in a slightly different fashion. We could have instead used the laws of logs in this way. Specifically, I want to use the law of logs. I also want to, I want to isolate this. I'm going to box this in green right here. The law of logarithms, though, that I'm suggesting that we can use, okay, would be the one that says that when we have a log with a base that is different than the base of the exponential, it allows us to pull the exponent to the front. That law of logarithms. And so I'm going to go ahead and apply, for example, just the natural log. I would do it with either the log base 10 or a natural log because I'm getting ready to go to the calculator anyway. Okay. So we have the equation 2 to the 1 minus x is equal to 3, and then I apply logarithm, the natural log in this case, I'll apply to both sides of the equation. Okay. Now we have a logarithm whose base is different than the base of the exponential, right? So we can use this law right here. That is, we can pull the exponent. Okay. Let's see. Here we go. We'll go blue. That is, I can pull the exponent, which is 1 minus x, to the front of this logarithm. So we now have parentheses, right? We have the quantity 1 minus x times the natural log of 2 is equal to the natural log of 3. Now, the natural log of 2 is just a number, so we can divide both sides of the equation by that number, natural log of 2, and we get 1 minus x is equal to the natural log of 3 over the natural log of 2. All right, and now we can, let's say, I can add x to the right-hand side and subtract the natural log of 3 over natural log of 2 from the 1. So we get 1 minus the natural log of 3 over the natural log of 2 is equal to x. But that's exactly the same answer that we got otherwise. Okay, so the two approaches are, because we didn't even have the option of converting to the same base on both sides, right? The options were we could either approach this by converting from the exponential form into the logarithmic form. This required that we had an isolated exponential term, that there was only one exponential term we were looking at, and it was isolated. That's a to the x is equal to y. We could convert to the logarithmic form, or also requiring that we are in that form where it is an isolated exponential, we can apply this law of logarithms, whereby we can apply a logarithm to both sides of the equation. Any base logarithm we want. We could have chosen a base 2 logarithm if we want it. The justification for choosing a natural log or a log base 10 is to be prepared for doing the approximation. If we're asked or required to approximate with a decimal, we already know that we're going to be going to the calculator anyway. If you want an exact answer, in all cases, if you want an exact answer, the point is to leave the calculator alone and to just express the solution, okay, in its exact form, as simplified as you can get it, okay, with the logarithm built in. Now, so you could write it as 1 minus log base 2 of 3. That is an exact answer. But in fact, 1 minus log 3 over log 2 is also an exact answer. And 1 minus natural log of 3 over natural log of 2 is also an exact answer. These are all, okay, these are 3 exact answers that we could write, and they would all be marked correct as an exact value. But the approximation, okay, the approximation is done by making sure that we have the appropriate base to access the calculator's functions, okay, and make sure we do the rounding correctly as well. Okay, so let's take a look at another example here. How about a logarithm example? Solve 4 minus the log of 3 minus x equals to 3. Okay, so it's a logarithmic equation, and the general strategy is to start by isolating the logarithmic term. If there was more than one log term, then we would want to combine into a single log. But in this case, we have only one logarithmic term, so we just want to get that term isolated. By isolated, I mean I want it to be the only term on one side of the equation, and I also want the coefficient of it to just be a positive 1. So let's get this isolated. I'm going to start by subtracting 4 from both sides. So I have negative log 3 minus x is equal to negative 1 after subtracting 4 from both sides. And then I'm going to multiply both sides by negative 1, so we get the log of 3 minus x is equal to 1. Now it is isolated. Okay, after isolating the logarithm, then what we do is we convert from logarithmic form to exponential form. Again, the conversion is done by the definition of the logarithm. If we have something log base a of x is equal to y, that gets converted into a to the y is equal to x. All right, so let's convert our logarithm. We have a base 10 logarithm in this case, so 10 to the power of 1 is equal to 3 minus x. And now we reassess the new equation and solve it depending on what family it belongs to. This equation happens to be linear, so we solve it as a linear equation. 10 equals 3 minus x, subtract 3 from both sides, 7 equals negative x, therefore x is equal to negative 7. And that's it. Remember to check your solutions, particularly with logarithmic equations. Okay, you have to check because you might end up with extraneous solutions. There's restrictions to the domain here. What is the domain? Okay, on the left-hand side, the expression on the left-hand side has a domain. It can be found by taking 3 minus x greater than 0. That is that 3 is greater than x. That is that x is less than 3. Or from negative infinity to positive 3 open. That's the domain. Well, negative 7 is a value of x that is in that domain. So that seems reasonable. Now let's just check to make sure. So this would be 4 minus the log of 3 minus negative 7. Is that going to equal 3? Okay. So this evaluates as 4 minus the log of 10. Does that equal 3? And what's the log of 10? The log of 10 would be what exponent would you choose so that if you raise the base of 10 to that exponent, the output would be 10. In other words, 10 to what power is equal to 10? And that power would be 1. So the log of 10 is equal to 1. And 4 minus 1 does equal 3. So that's correct. So our solution is correct. It is also not extraneous. Okay, and it is the only solution. All right? So we isolated the logarithm. That is, including that the coefficient of it became just a positive 1. Right, in this case, we multiply both sides by negative 1. So you can multiply, you could divide both sides by negative 1. You could use the law of logarithms that says that you can pull the coefficient up to the top. We could have written this as log of 3 minus x to the negative 1 equals negative 1 if we wanted to. Okay, and then we could have rewritten this in exponential form, right? But I think the most straightforward way to do it was the way that I showed right here. Feel free to try other approaches as you wish, to see what works best for you. Okay, let's try another exponential example here. I would like to try one whereby there's an exponential on both sides of the equation. Let's say, for example, 5 to the x is equal to 7 to the x minus 2. Right? So the two sides, we cannot write both of them conveniently or easily with the same base on both sides, like we could earlier when we had a 25 on one side and a 5 on the other for the bases. Okay, so we can't get same base. But what we can do is we can isolate each of these exponentials independently. They are already isolated. We can apply the logarithm to both sides. Okay, and so essentially writing this in the logarithmic form. So I'm going to apply the natural log. Okay, apply the natural log to both sides, and then use the law of logarithms. It says that when you choose a base logarithm which does not match the base of the exponential, we can pull the exponent to the front, and that is rewrite the exponent as a factor. So we can rewrite this as a product. Okay, so this says we can choose any base logarithm we want. So I'm choosing the base e logarithm. Okay, so natural log of 5 to the x equals the natural log of 7 to the x minus 2. Then, by this law of logarithms, we can pull the exponents to the front of each one of those logarithms. So I have x times the natural log of 5 equals the quantity x minus 2 times the natural log of 7. I need to see those parentheses there. If the parentheses are not there, then it's not correct grammatically in the language of math. Those parentheses are required. So we have x times the natural log of 5 equals the quantity x minus 2 times the natural log of 7. What kind of an equation is this that we're actually looking at here? We reassess this. That this is not a logarithmic equation anymore. The natural log of 5 is just a number, and the natural log of 7 is just a number. Okay, they are irrational numbers, so they're not going to be convenient decimals, but they are just numbers. Where the variables are not contained within the logarithms themselves. And if we look at the variables, they are all to the power of 1. So in fact, this is a linear equation that we have to solve here. And we know how to solve every linear equation we would ever see. So we should be able to solve this, even though it has weird numbers in it. How do you solve a linear equation? We can isolate the variable. Okay, so I'm going to start by combining the terms that have a variable in it, that have the x in it. So, in order to do that, I need to expand on the right-hand side by distributing. So we have on the right-hand side x times the natural log of 7 minus 2 times the natural log of 7. Now we can subtract x ln 7, okay, onto the left-hand side. So we have x times the natural log of 5 minus x times the natural log of 7. And that's going to equal negative 2 natural log of 7. Now we have two terms on the left that have x in it. I'm going to factor out the x. So we have x times the natural log of 5 minus the natural log of 7 equals negative 2 times the natural log of 7. So one way we can write this answer as an exact answer is to write x equals negative 2 times the natural log of 7 divided by the natural log of 5 minus the natural log of 7. Okay, and that would be an exact answer right there. The exact answer written this way. Some other ways. By using laws of logarithms, we can sort of clean this up a little bit. We can say that this is also equal to, okay, using the law 3 of logarithms, we can move this negative 2 coefficient here. We can move it to the exponent of the argument. So we can rewrite the numerator as the natural log of 7 to the negative 2, which is the same as saying 1 over 7 squared, or 1 over 49. Alright, so we can write this as the natural log of 1 over 49. It's just another way of writing the exact same quantity, and it's still exactly equal to what we started with for the numerator. And the denominator, we have the natural log of 5 minus the natural log of 7. By law 2, the second law of logarithms, we can combine those two as a natural log of 5/7. Okay, so those are other ways that we can write the exact answer. How about an approximation? Okay. Let's approximate the solution to 6 decimal places. Any one of these we can enter into the calculator. Okay. Just make sure that whichever one you enter, you get the same answer. Okay, so watch your parentheses in the calculator so that it can follow the order of operations correctly. For example. Okay, so I'm going to enter this one in the calculator right here. See if that's it. And of course we can check our answer afterwards and see if it's reasonable. We're using an approximation now. So the natural log of 1 over 49, closing the parenthesis then, dividing by the natural log of 5/7. Okay, so I'm getting that is approximately, let's see, 11.56654212. So to 6 decimal places, 1, 2, 3, 4, 5, 6, okay, to right here, okay, this is going to be approximately 11.566542. That's our approximation to 6 decimal places of accuracy. Okay. And we can check this answer in the original equation to see if it works. So the original equation, 5 to the x is equal to 7 to the x minus 2. What was the domain of that equation? These are both exponential, right? So recall that the domain is actually all real numbers. Okay. But the range, however, the range would be 0 to infinity. But the domain is all real numbers, so all values of x are possible. But we want to make sure that the outputs are going to match as well. So let's just check the answer for good measure here. Okay. I'm going to check. We're going to use our approximation to check. So the two sides might be almost equal to each other, but not exactly equal to each other. 5 to the x is equal to 7 to the x minus 2. Okay, we're going to plug in this approximation. So 5 to the power of 11.566542, is that equivalent with 7 to the power of 11.566542 minus 2? So I'll go to the calculator and find out what 5 to the power of 11.566542 is equal to, and I get this massive number here, 1215,25079. So that's what, 121,525,079. Okay, is that equivalent to the right-hand side? Well, the right-hand side is 7 to the power of 9.566542. Okay, so I'll try that in the calculator. 7 to the power of 9.566542. All right, and the value I get on the right is 1215,25073.9. 121,525,000. Okay, and then I got 73.9. Okay, this is good demonstration of how even when we round it to 6 decimal places here, the power of exponentiation, right, of exponential growth, okay, caused our two sides to creep farther away from each other. So we did not get, well, let's see, we were precise to 1, 2, 3, 4, 5, 6, 7, at least 7 digits of accuracy, okay, because this would have rounded up to an 80 here, but this would have rounded down to a 70 here. Okay, if we wanted more, if we wanted to get more accurate results here, better precision, we should go even more decimal places in our rounding here. And we certainly could have. We could have gone further than that. Okay, but we can see that the process worked, right? The two answers are pretty close to each other. Let's see, I have e to the x plus 15 e to the negative x. Minus 8 is equal to 0. Okay. All right, so we've just increased the complexity here. Okay. In general, the strategy is to isolate the exponential term. But we have more than one exponential term here. And we can't combine exponential terms the way we can combine logarithms. Okay. So what else can we do? And we should take a look to see if there's some other strategy that we can apply. Okay. Take a look. Can we use factoring? Okay? Can we use some other kind of a technique? Substitution, for instance. Like, can we say that, both of these could work here? Let's take a look at multiple approaches here. Okay? Let's say I rewrite this with positive exponents, for example. So this middle term here I can write as 15 over e to the power of x minus 8 is equal to 0. So that makes this look a little bit more like a rational type of an example. It's not truly rational because we have an exponential down there, not a polynomial. Okay, but we have a denominator that has a variable expression in it. So we can use an approach that we would use in a case where if it were rational, which is we can multiply by the common denominator. So if we multiply both sides now by e to the x, and we can distribute e to the x, well, what is e to the x times e to the x by rules of exponents? Right? That is going to be e to the 2x. You would add the exponents together. Okay, so in distributing, we're going to get e to the 2x plus 15, because there e to the x cancels e to the x, minus 8 e to the x is equal to, well, 0. Okay, also e to the x times e to the x can be written as e to the x quantity squared. Right? So it's something squared. So in fact, if we rewrite this in descending order of the powers, we have e to the 2x minus 8 e to the x plus 15 is equal to 0. Right? Or e to the x squared minus 8 e to the x plus 15 is equal to 0. Right? And in either case, if we take a closer look, by inspection, we see, well, the exponent here is double the exponent here, and this term is constant with respect to x. All right, so we have three terms, okay, with this pattern. Okay, that means that we have something that is quadratic in form. All right, we note that this equation is quadratic in form. So we can treat it as a quadratic. That is, we can use the quadratic formula, or we can try to apply factoring strategy. How would we be able to factor it? Okay. We might choose to just try to factor it directly. That's fine. We can write that we have a product of two-term expressions, where, for instance, we would have e to the x as the leading term in each, because e to the x times e to the x is e to the 2x. And then we can find integer values that would multiply to equal 15, but that would add up to equal negative 8, since our leading coefficient here was 1. And that would be minus 3 and minus 5. And that's it. Okay? If you didn't want to factor it that way, you could choose a substitution. And the substitution we could choose would be, in this case, for example, to let u equal to e to the x. Right? And then if we take this form right here, if we replace every instance of e to the x with a u, we would get u squared minus 8u plus 15 is equal to 0. And then we get what is, a more traditional looking quadratic in standard form. Right? Standard form quadratic equation, that is. And then we can solve that one by factoring. And if we didn't want to do the factoring, or if we couldn't factor, we still would be able to solve by the quadratic formula. We could do u is equal to 8 plus or minus the square root of negative 8 squared, which is 64, minus 4 times 1 times 15, okay, over 2. Okay? And if we did that, all right, if we could not factor, this is what we would have to do. Notice that in terms of x, what we're actually doing is we're finding out values for e to the x. When we solve this quadratic form, when we simplify this expression over here, we would get, potentially two quantities in general over here. It would be that e to the x is equal to those two quantities. What are those quantities going to be in this case? We're going to get e to the x is equal to either 3 or e to the x is equal to 5 in this case. Right? Just like we would by factoring right here. You set each of the factors equal to 0, and you solve. E to the x is equal to 3, or e to the x is equal to 5. And so we get two more basic exponential equations, and then we can solve each of those independently. All right. Okay, so I multiply by e to the x, regrouped the terms, okay, let's change the order, commuted the terms, recognize that we in fact actually had, disguised here, we had a quadratic in form equation. So we set it up as a standard form quadratic equation, that is descending order of the powers. We had a trinomial. All right, this exponent was double that exponent, and this was a constant, and we had it equal to 0. That's standard form quadratic in form. We could factor from there, we could choose a substitution, like u equals e to the x would have worked. Okay? We could use the quadratic formula if we wanted to, where we could set e to the x equal to the expression from the quadratic formula. Okay? In any case, we end up with two basic exponential equations, and we can proceed by solving those two equations. To solve this either of these equations, we would apply the simplest way would be to apply the natural log to both sides. In other words, convert it into the logarithmic form. So we take natural log of e to the x is equal to natural log of 3. Since the base and the exponential have the base of the logarithm and the base of the exponential are the same, they cancel each other, right, by a property of logs. So x is equal to the natural log of 3. Okay, is one potential solution here. And that's an exact solution, by the way. X equals natural log of 3. Applying the same technique to the other side, natural log of e to the x is equal to 5. Therefore, x is equal to, sorry, a little too fast there. Natural log of e to the x is equal to the natural log of 5. Therefore, x is equal to the natural log of 5. Okay, we can check each of these in the original equation. What's the domain of the original equation? These are exponentials. The domain is all real numbers. Negative infinity to positive infinity. So these are both possible solutions, and we can check to see if they're true. So let's try to plug into the original equation then. Let's start by checking x equals the natural log of 3. And the original equation was e to the x plus 15e to the negative x minus 8 equals 0. Plug in x equals natural log of 3. E to the natural log of 3 plus 15e to the negative natural log of 3 minus 8 is equal to 0. Check to see if that's true. E to the natural log of 3, recall that a to the power of log base a of x, that is, if the exponential and the log have the same base, they cancel each other out. So e to the natural log of 3 is just 3. E to the negative natural log of 3, okay, well first take a look at the exponent and recall that if we have c times log with a base that does not match the base of the exponential, right, if these don't match each other, by law of 3 we can move that factor to the exponent. So this is log base a of a to the c. Okay, so I can rewrite e to the negative natural log of 3 as e to the natural log of 3 to the negative 1. But 3 to the negative 1 is 1/3, so I can rewrite this as e to the natural log of 1/3. And then minus 8, does that equal 0? And now, by the same property of logarithms that I used over here, right, the e and the natural log are going to cancel each other out. So we have 3 plus 15 times 1/3 minus 8. Does that equal 0? 15 times 1/3 is 5. 3 plus 5 minus 8. Yes, that does equal 0. Okay, so natural log of 3 is going to be a solution to the equation. Now let's check x equals natural log of 5. All right, so e to the natural log of 5 plus 15e to the negative natural log of 5 minus 8. Does that equal 0? E to the natural log of 5 is equal to 5, and then plus 15e to the negative natural log of 5, That's e to the natural log of 1/5. Okay, so we get 5 plus 15 times 1/5 minus 8. And that's going to be true. 15 times 1/5 is 3. 5 plus 3 minus 8 does equal 0. So that's true. So both those solutions are valid. Okay. Another equation of exponential type, but a little bit different. X squared times 2 to the x minus 2 to the x is equal to 0. Isolate the exponential. How do we do it in this case? Since there's more than one. Try factoring. These two terms share the greatest common factor of 2 to the x. So we can factor out 2 to the x. That's an effective strategy given that the right-hand side is just equal to 0. Take out 2 to the x, we are left with x squared minus 1. And that's equal to 0. Alright, let's make a note of the domain here, just to be sure. Alright, the domain is negative infinity to positive infinity. So all values of x are possible. All real numbers x are possible here. So now we have a product of factors equal to 0. So we can set each of the factors equal to 0. That is either 2 to the x is equal to 0. Let's take a look at that in a moment. Or x squared minus 1 is equal to 0. And that's quadratic. Pretty easy to solve too, right? X is equal to plus or minus 1. Okay, so we have two potential solutions there to check. 2 to the x is equal to 0. What do we know about 2 to the x? First of all, analytically, if we take a look at the graph for the function y equals 2 to the x, notice, of course, it never does equal 0. It has a horizontal asymptote. A horizontal asymptote is y is equal to 0. That is, it never reaches y is equal to 0. Okay, so there's no solution to this. Now we can also figure that out symbolically by applying the technique. For instance, let's say we apply logarithms. If we take the natural log of 2 to the x equals the natural log of 0. Okay? Well, natural log of 2 to the x is the same as x times the natural log of 2. But the natural log of 0, that's undefined. Okay, but x times the natural log of 2, okay, in order for that to be undefined, then it means that x is undefined. So there is no value of x. Okay, there is no solution then. Right? The log of 0, right, does not exist. Right? Why does the log of 0 not exist? Log base a of 0, okay, is undefined. Because if we tried to make it equal to something, let's say I tried to make it equal to n. Let's say there was some number that this was equal to. Okay, if that was true, by assumption, then it would have to be that a to the power of that n is equal to 0. Okay? But a to any power is never equal to 0, as can be verified by looking at the graph. We are approaching a horizontal asymptote. We know that this never reaches 0. Okay, but a to the power of n does not equal 0, right, for any n. So, log base a of 0, you say, does not exist. Okay, does not exist. In other words, it is undefined. You cannot take the log of 0, no matter what base you select. Okay, because there is no exponential that would output 0. For any base or for any exponent. So 2 to the x is equal to 0, no solution to that. That's not possible. But x squared minus 1, that can equal 0. So we have two potential solutions here, x equals 1 and x equals negative 1. And we can check those solutions. Let's check x equals 1. In the original equation, that is 1 squared times 2 to the 1 minus 2 to the 1, does that equal 0? In other words, 1 times 2 minus 2, does that equal 0? Yes, it does. What about negative 1? X equals negative 1. Okay, the original equation, that would be negative 1 squared times 2 to the negative 1 minus 2 to the negative 1, does that equal 0? Well, that's 1 times 2 to the negative 1. okay, which is 1/2. Okay, 1/2 minus 1/2 does equal 0, so that's true. So both x equals 1 and x equals -1 works in the equation here. Okay, so we were able to isolate the exponential by factoring it out as a greatest common factor. Okay, so using a factoring strategy, and it even led to a result that, there was to an exponential equation that didn't have any solution to it. Although the original equation still had, in fact, 2 solutions, which came from a quadratic factor. Okay, how about we take a look at an application? More applications to come in the next section, but we can already take a look at one now. For instance, how about compounding interest? If we were to solve for the exponent in a compound interest problem, find the amount of time until, an investment of $5,000 grows to $8,000 at 7.5% APR, annual percentage rate. Now let's do compounding. All right, we could do compound it periodically. We could do compound it continuously. We know how to solve this problem in either case. Let's say we compound it quarterly for this example. So when we're compounding quarterly, that means that n is equal to 4. That is 4 times per year, and we have an annual percentage rate. Okay, so the units of time are matching up. All right, 4 times per year, the 7.5% per year. So the amount of time we're going to be solving for would also have to be in years. Okay, so the units of time are all matched up. And the formula we need when we're compounding with a finite number of compounding periods is a, or in fact, as a function of time, a of t is equal to p times 1 plus r over n to the power of n times t. And we are solving for t, and t is in the exponent. So we're solving an exponential equation, and for that reason, we should expect we will need to use logarithms in order to do so. Let's see, so we might get a weird answer here. So let's round to 2 decimal places. Okay, we could say that, or we could say, because we're doing this in years, we could say round to the nearest quarter of a year, or round to the nearest number of months. Give the answer, approximate it with the number of years and number of months, or something like that. We'll say just round to 2 decimal places, but our answer will be in years. Let's plug in what we know into our equation here. We have an investment that is initially $5,000, so the value of P would be 5,000. That's the present value. And we want it to grow to $8,000, so 8,000 is the future value. That's the amount of A. 1 plus R. R is 7.5% APR. That is the decimal 0.075. N is equal to 4 because this is quarterly compounding. And the exponent is n times t, so that would be 4t. All right, and our task is to solve for t, which is in the exponent. How do we do that? Let's start by isolating the exponential. Okay, the exponential term is kind of isolated here, but it still has a coefficient of 5,000. We need to kick that out of the way. So I'm going to start by dividing by 5,000. Okay, divide both sides by 5,000. 8,000 divided by 5,000 would be 8/5. So 8/5 is equal to this quantity 1 plus 0.075 over 4 to the power of 4 times t. Okay, and this is an exponential equation of the type a to the x. Okay, well, it's written this way: y equals a to the x. Right, we have a variable exponent. Right now it's 4t is the exponent. We have a constant base, this 1 plus 0.075 over 4. Yeah, 1 plus 0.075 over 4 is our constant base. And we have an output, 8/5, which is a constant as well. We can solve that by using logarithms. Right? The log base a of y is going to equal x. That is, we can choose the base of the logarithm to be the number 1 plus 0.075 over 4. That's a strange number to choose for a base, and we could do that. But we should expect that, in this case, we're going to want to go to the calculator. After all, we're going to want to round to 2 decimal places in this case. So if I'm going to go to the calculator, I would rather choose a logarithm that the calculator can deal with. That is either a base 10 or a base e logarithm, and it doesn't matter which one you choose. But we're dealing with decimal numbers. I'll just choose a base 10 logarithm instead. Okay. So we could do that, okay? But in general, we're just going to use logs. Okay. So I'm going to take the log of 8/5, and you could certainly use the natural log instead if you would rather use the natural log. That would be fine. It would also work. Okay. So the log of 8/5 is equal to the log of 1 plus 0.075 over 4 to the power of 4 times t. Okay, now we can use the law of logarithms, okay, to pull the exponent to the front. All right. So we have the log of an exponential. We can pull the exponent to the front, like so. And the exponent here is 4 times t. So we have the log of 8/5 is equal to 4 times t times the log of 1 plus 0.075 over 4. Now, what kind of an equation do we have right now if we assess this equation? The log of 8/5 is just a number. The log of 1 plus 0.075 over 4, that is in fact just a number. And 4 is just a number. And the only variable that we have, t, is to the power of 1. So in fact, our equation here is just a linear equation. And we can solve it for t by just dividing all of the factors that are multiplied by t. All right, so we can isolate t by dividing both sides by 4 and dividing both sides by this logarithm here. So we get the log of 8/5 divided by 4 log 1 plus 0.075 over 4. This is all just a number here. And we can go now to the calculator to find out an approximation for that number. So all this into the calculator. If you would use the natural log, it would look very similar to that, and your answer is going to come out the same anyway. So I have the log of 8/5, and I close the parenthesis in the calculator, and I'm dividing. Now in the calculator, after dividing, I'm then including another parenthesis. Okay, so the calculator knows I want to divide by all of this. If we didn't do a parenthesis in the calculator, it might only, it's set to only divide by the 4, and then it's actually going to multiply by this instead. Okay, so log of 8/5 divided by parenthesis 4 log, and then 1 plus 0.075 divided by 4, and then close those parentheses off and hit equals. So I'm getting 6.325, and then 2, 8, on and on and on, and that's an approximation for t, which is an amount of time measured in years to 2 decimal places. Then the 5 says to round this up, so 6.33 years. Okay, so about 6 1/3 years. Right, or 6 years and 4 months is what that would be. is how long it would take for this account to grow $5,000 to $8,000. Okay, 7.5% interest. And we can check our answer here by plugging the 6.33 back into the original equation. Checking to see. And for good measure, we should check. Does 8,000 equal 5,000 times 1 plus 0.075 over 4 to the power of 4 times 6.33? And this is an approximation, so it may not come out to exactly 8,000. In fact, it's not going to come out to exactly 8,000. But it should certainly be very close to 8,000. Reasonably close to 8,000. So I'm going to evaluate the right-hand side on the calculator. 5,000, okay, times quantity 1 plus 0.075 divided by 4. Close that parenthesis. And then on the calculator, I'm going to raise to the power of parenthesis 4 times 6.33 on the right-hand side, like that. All right. Okay, if I didn't include these parentheses here, then it's only going to raise it to the power of 4, and then it's going to multiply that whole result by 6.33, which is something different than what we're saying we want. So 4 times 6.33, okay? And yeah, so on the right-hand side, then I'm getting that this is approximately 8,002.804, okay? So it's a little bit more. It's a little bit more. Why is this a little bit more than 8,000? Well, the exponential function, the exponential growth function is an increasing function, and we rounded this number up. So we rounded the exponent up, okay? And on an increasing function, if you increase the value of x, you will increase the value of y. That is, if you increase the input, you expect to increase the output. And that's why this number is more than $8,000 by rounding this up. So that's reasonable. Okay. If we had gone out to more decimal places of accuracy here, right, we should expect to get closer to the $8,000. Okay. Now, what if we did this with continuous? Okay. What if we did this with continuous compounding? Same question, but with continuous compounding, then the model we would choose, A of t is equal to PERT, P-E to the power of r times t, because we have, by continuous compounding, we're saying n is approaching infinity, and that gives us a base of e then. Okay, solving for the amount of time in that case, we have the equation is what? 8,000 is equal to 5,000 is the principal. E is the constant e that we're aware of. R is 0.075, and then we have t, which is also in the exponent. Same strategy to solve this exponential equation. You're going to isolate the exponential. That means it starts by dividing both sides by 5,000. So we get 8/5 is equal to e to the power of 0.075t. Okay, then we want to get log form. That is, apply the natural log. The natural log of 8/5 is equal to the natural log of e to the 0.075t. When the base of the logarithm and the base of the exponential are the same as each other, they cancel each other out. So the right-hand side becomes 0.075t, and the left-hand side is the natural log of 8/5. Now we can just divide both sides by 0.075. So I get natural log of 8/5 divided by 0.075 is equal to t. So let's approximate t to 2 decimal places of accuracy here. Okay, we're now compounding continuously, so we can expect that the investment, the principal, is going to grow. Okay, is going to grow to the goal of $8,000 at a faster rate. So this conceivably will take less time than it was when we were compounding 4 times a year, because we are now compounding in an uncountable number of times per year. So I expect for this to take less time since it's growing at a faster rate. Let's see how much less. All right, so you take natural log of 8/5 and divide that by 0.075. and I get t is approximately 6.2667. So to 2 decimal places, we would have 6.27 years is approximately t. It is less time, but it's not a lot less time. Okay, it's just 6/100 of a year less. Right, so maybe 3 weeks or so less. Okay. And you could check that answer by plugging that value of t back into this equation here and seeing how close this is to 8,000. Okay. So that should do it for this section. You have a couple more application problems to look at in the homework. Let me know if you run into any issues with those, if you need any other assistance. And we'll be moving ahead then into exponential modeling in the next section. So that's it for this section. Okay, let me know if you have any questions. Okay, take care.